My name is Eric Anderson. I specialize in anaerobic digestion, and today's focus is on the meat industry, kind of their wastewater and slaughterhouses, anything that deals with a high BOD, high COD wastewater stream, and its potential for heat generation electricity. Today, we're going to do a high-level overview, anaerobic digestion of this material. I'm going to look at the high-level process overview, what's involved. We're going to look at the meat and livestock processing waste specifically and how it's suitable for anaerobic digestion, more so than a lot of other materials out there that are actually currently being digested, in fact. And we're going to talk about some of the material pre-treatment that's required specifically to material coming from meat waste industries. It is unique. Like I said, there's benefits to it, but there's also barriers, as with everything, and feedstock control, how we can integrate these operation facilities into a 24/7 operating anaerobic digestion system. Another big topic is how can the meat processing industry benefit from this? That's going to be a big point to discuss. Why do it if there's not going to benefit you either in cost or energy savings? We will focus a bit on the barriers, like I said, of this material, of slaughterhouse waste. We'll look at different types of technologies out there that are kind of targeted for this waste stream specifically, anaerobic lagoons and CSTRs, which are continuously stirred tank reactors in some cases. We will look at the valorization of the biogas. What are the end uses? Is it going to be on-site thermal use? Is it going to be to generate electricity? Is it to be to produce renewable natural gas? I will mention some of the state and federal incentive programs that are currently working in collaboration with rural and industry efforts to either reduce their energy usage or produce renewable energy. And at the end of it, we'll have a slide on kind of the early development stages through design and engineering and commissioning of one of these systems, what it looks like at one of these sites. First slide I have, anaerobic digestion. What is it? Let's just define it right out of the gate as a biological process where microorganisms break down organic matter. They do this without any oxygen present. It's inhibiting in this case, and the goal is that the organic matter in liquid phase turns into a gas. This gas is very rich in methane and CO2. That gas is driven out of the liquid phase and above the liquid where it's captured. Again, we're covering these systems so that there's no air or oxygen present. That gas is collected, pumped out of the system, and utilized some way for energy. One thing to define here is the biological oxygen demand. This is a very common metric for wastewater treatment, and it ultimately says it's a measure of how much oxygen is consumed by microorganisms in this to decompose organic matter. It's a great measure of, A, what's your concentration of waste in your liquid stream, and there's also a measure of what's the biogas potential in that liquid stream. There's lots of waste in this, pollutants that can't be converted to organic matter. They can't be converted, to gas. It's either organic in nature but recalcitrant and can't be broken down, or it's inert but can be oxidized. So it's very critical to define what's in there and what's actually of value. Keep forgetting. How can the meat industry benefit from anaerobic digestion? So we've defined what it is, breaking down this organic molecules to make energy, make a gas energy, a molecule of methane. But the benefits to the plant would be, the first would be water treatment cost reduction. You as in meat handlers, meat processing agencies have a wastewater stream. It's usually a combination of wash down waters. It can be processed water. It can be spray water. It can be manure coming from holding cells. But there's a collection of water every day, usually very large for certain facilities, can be into the millions of gallons a day, that has a dilute but high BOD concentration, high organic concentration. Anaerobic digestion, by its nature, can help break down those organic materials on site so that less material is sent off to be processed at a cost, either in water treatment facilities or sold off as a not value-added material, but as a waste material that needs remediation. Another benefit, on-site energy generation. Once you produce this methane, you can do something with it. You can convert your boiler systems, you can make electricity on site, or you can convert to renewable natural gas and put it into our national pipeline. So there's options. Another benefit would be the value added of the final digest date. So rather than treating this stuff, you've got a waste organic material. It can have pathogens in it. It's not readily available to put onto landfills. But the amount of nutrients that go into that are not degraded during anaerobic digestion. So whatever goes into it comes out of it, but just at a reduced mass. Because of that, this material is a pretty value-added byproduct to go onto land for fertilizer remediation. And the last potential is, one thing is specific to this industry, because it's high in protein and ammonia. We'll talk about that later. Or it's high in protein, nitrogen, and thus can make a lot of ammonia. Ammonia recovery is an option that is becoming more popular. It's used throughout Europe, and there's technologies trying to move forward into the pig and chicken manures industries here in the US, to create a pure ammonia byproduct. It's not a derivative, it's actual ammonia, stripped from the system and sold as a fertilizer offset. Here you can see a map of the top agricultural animal products by state in the US currently. And the big draw, the takeaway from here is you can see the red and blue are beef and dairy farms respectively. So the far west half, or the whole west half of the United States, the dominant animal species is cows, mixed between beef and dairy. Whereas chicken and livestock, chicken and poultry are on the southwest corner, and other livestock, I'm not sure how they define that, is spread throughout. But chicken, yeah, Midwest, Minnesota, Iowa, Illinois, and then Southeast. And the one thing to take away is the regionality to a lot of this production, where you would find certain technologies, where you'd find certain trends in, anaerobic digestion, wastewater treatment processing specifically, and how anaerobic digestion could fit into that. Common meat processing streams. So when we're talking about meat processing industry, livestock, there's a lot of different industries that this topic can touch on. It's any meat industry or any processing industry that deals with a lot of meat, high protein, a lot of blood, protein derivatives, a lot of high oil content from rendering operations. But ultimately, you can categorize into waste meat processing, wastewater, which would be the wash down, like we talked about, water, the DAF, which is the dissolved air flotation unit, the effluent leaving that, or in a lot of cases, we've looked at using the DAF solids, the material that comes off. In that case, if a system already had a DAF unit, depending on the chemicals they'd use for it, we could retrofit and go in front of that unit or behind it and target one of those streams. But both materials are prime organic concentrated streams that can be fed and broken down by anaerobic bacteria. Ponch material, I've worked with facilities that were interested in, they had offtake agreements currently with their ponch material, but they were interested in processing it in a digester. That material is very, thick and can be tough to deal with. It needs to be ground and pulverized and processed into a way that can be fed into a digester. Animal manures obviously are very popular, each bringing their own uniqueness in terms of design and processing. Chicken and pig manure being heavier in protein concentration, being higher in nitrogen specifically, that leads to ammonia. But again, dairy and beef cows can have the same issue. Waste oil collection, rendering operations, dead cow mortalities have a lot of waste products, meat and bone meal products, grease, waste traps. This stuff is high in fats, oils, and grease. Although there's a limit to how much that can be blended into a feedstock, it is very beneficial. We'll talk about the reasons for that later on. And again, any industry that has high oil protein base in its processing, food industries that deal a lot with fryer material, fryer grease, often have a high BOD wastewater that needs to be dealt with. These are all industries that in theory should address the potential for anaerobic digestion. It's not necessarily that is the correct pathway for them, but there's a lot of potential here. We'll talk about why. The one thing to take away from this slide, that not all feed is created equal. And this is where I'm going to start discussing how the slaughter industry and how their waste product is different from other products that are most commonly anaerobic digested. Food waste, you can see on the left here, the blue is the water content. It can range heavily, but a lot of food waste innately, before they're mixed with a wastewater, can be high in total solids. To break it down here, the total solids is everything that's not water, ultimately. But within that solid content, there's degrees of usefulness. There's an inert portion of it that does not contribute to the biogas at all. It's inorganic mostly, can be organic. Well, it's inorganic mostly. Grit, dirt, windswept sand that's blown in to fields on farm manure, what have you. Of the volatile components, there's a total volatile solids, and then there's a portion within that called bioavailable volatile solids. And what that means is not all organic material can be broken down in the time necessary for a digester to operate. That material can be cellulosic. It can be just bonds that aren't broken down within the design time, and they move through the process rather inertly. So that greenish, the light green portion is what we're actually interested. And again, the takeaway from this slide is on the far right is the slaughterhouse waste. And the big thing to notice is that there's much less total solids in here than there would be food waste coming from a factory or animal manure being scraped out of a barn. That is not as it's not bad or good. It's just the nature of the material. What it does is kind of define food waste and animal manure as more energy potential producers. And slaughterhouse traditionally has been kept in this waste remediation effort, kind of a treatment focused anaerobic digestion. Today, and one of the exciting things about this talk is why I think there's a lot of potential for slaughterhouse and this type of waste material to be the new focus of anaerobic digestion in the next couple of years. As some of you may be aware, animal manure was the largest kind of sweep of anaerobic digestion systems going up in the US. Large farms are targeted, and pretty much to date, the largest farms all have some form of anaerobic digestion on them, along with food waste. Food waste because of the revenue potential with tipping fees and taking in other people's waste. But to date, one of the things that is kind of held back is a lot of the industrial anaerobic digestion to energy systems. So again, I think that's why slaughterhouses and a lot of these systems that produce high temperature waste that we'll go through are the next kind of wave of systems to come online. To go through the bullet points of the common characteristics of these wastewater types coming from all different industries. The first one is high protein. Slaughterhouse waste has a lot of blood. It's got a lot of muscle, a lot of meat, waste derivatives, I guess you'd call them, breakdowns. But this stuff is, because of the nature of protein, we'll talk about that, a lot of nitrogen comes in with it and a lot of sulfur. These things, without design intention, can be problematic. They can be inhibiting agents. They can slow your production, if not kill it, if left unchecked. The other major characteristic that we talked about is the low total solid content. The higher discharge temperatures, this is a very common industry characteristic of a lot of slaughterhouses, a lot of meat processing, that their wastewater might come out at above 100 degrees Fahrenheit. That can be a huge benefit. With that high temperature, you can get a high soluble degree of what's called chemical oxygen demand or biological oxygen demand, BOD, that we talked about. This is essentially a measure of the amount of oxidizable material in solution. The low inert content, you can see on the graph here that along with low total solids is a very low percentage of inert character, because again, the material comes from essentially cow organic and stomachs and meat and blood. There's not a whole lot of bone. There's not a whole lot of grit. These are systems that are contained within factories that are usually well regulated. So the only inorganic material would be the material coming from a body, the animal processing plants. Usually a lot of these facilities we've been to already have some form of water treatment, and anaerobic digestion can literally integrate some way into that in some cases, with minor retrofits, sometimes with larger design considerations for pre-treatment. Next one is the barriers associated with the AD material. We can't talk about the positives without talking about the negatives. The high protein feed that we talked about comes with negatives. The ammonia concentration, if not dealt with, if it comes in and it rises above in steady state conditions, which just means the concentration in the digester at any one time raises about a certain limit, the bacteria become inactive, less active to a point that they become completely inactive. It's called inhibition. The sulfur that comes in with the protein as well can turn into hydrogen sulfide. Hydrogen sulfide is another inhibitory agent, both in the gas phase to the bacteria and the liquid, but also it needs to be dealt with in a gas recovery stage. So once you need that biogas, remove it from the system, it needs to be dealt with, removed for any processing. It damages equipment for electricity generation, boilers, or RNG. Salt concentrations. This can be a difficult one and needs to be addressed with every site specific. Salt can be used a lot in processing for meat, both in storage, both in the actual upfront processing, and then cleaning afterwards with salt solutions. They need to be addressed, especially with the logistics of a plant. This is one of the things that in design, matching maybe a operating facility that only operates 12 hours a day, 5 days a week with a 24-hour system. You need equilibrium, you need monitoring before you feed into these systems. So salt and fats, the next bullet point, high fat and oil concentrations both need to be understood. Their logistical output from the facility and how to buffer those into into a biological system. Same thing with disinfecting agents. A lot of these slaughterhouses are required to disinfect at certain rates, certain concentrations, and that needs to be accounted for. Both that it's not an antibacterial cleaner, so the system may need to turn over or change the type of chemicals they use, but it also needs to be, again, buffered out in a time scale when being fed to a system. So those are some of the physical limitations to the biochemistry of it. There's also design limitations. As I said, a lot of these facilities are prone to using low level technology systems like a lagoon, which makes complete sense because they're a waste remediation effort. They're not trying to force these numbers and these performance metrics to a certain level to pay off equipment. They're just trying to reduce the amount of organics they need to send to processing later on. Because of that, they often are left at the whim of less control, less monitoring, less operational optimization, and they can unfortunately reach failure points before their design limits. They can fill up with solids. Their certain equilibrium control points can fall off radar. So there are limitations between, is this a system meant for treatment or is this system made for energy production? I'm a big believer, and I think one of the really great things of having this webinar is that slaughterhouses, again, because of the high temperatures and a lot of the nature of the material, its high soluble BOD concentration, they would be a good fit for kind of a hybridization, kind of an improved lagoon model that has some of the features that would come from an above ground system incorporated into a lagoon system. And we'll talk about that. What operations are involved? So looking at this block flow diagram, you can see on the left, I start with any of the hypothetical feed substrates you could be coming from a plant a plant or livestock operation, processing operation, excuse me. DAF effluent, DAF solids, screen solids, paunch, cow manure. That should be any animal manure. I apologize. A lot of these slaughterhouses will have contained a day's processing in holding that manure gets trenched or collected and sent to wastewater as well. Pre-treatment, specifically for this industry, and is some degree of mastication, which is grinding chopper pumps into circulation. EQ tanks, again, that appears to be critical for this industry just to buffer out the operational highs and lows of the facilities. And that could be timing. That could be timing of CIPs, clean in place systems, disinfectant systems or schedules. But you want enough residence time in a holding system that can be mixed and homogenized. Because of that EQ nature, I've also seen a lot of systems interested or installing thermal hydrolysis systems. This is unique in that it's a form of anaerobic digestion tailored to a 5-day high temperature residence time. It's targeted at breaking down larger macromolecules, proteins into amino acids, sugar, carbohydrates into sugars, etc. But it speeds up that early work of digestion breakdown to feed more soluble material into the digester. But again, any degree of material processing or biological processing could be in that pre-treatment component for this material. And sometimes it needs to be different. Sometimes your DAF, that doesn't need to be run or equipment size to run all that material through it. It can focus on just the grinding and mastication on the paunch and the DAF solids or some combination of byproduct streams. But ultimately, everything ends up in anaerobic digester. It's processed. The biogas can be taken off separately to be processed individually. Today, we're talking about boilers used. And when I say boiler, I mean to be used on site. Most slaughterhouses, meat processing operations have a high degree of thermal load, and they burn natural gas in there. Those boilers can be retrofitted with relatively simple modifications to run on a combination of this methane and natural gas, and that allows you to offset your thermal usage. We'll talk in other slides here, but combined heat and power is another option for electricity generation, and then renewable natural gas. The digestate, what leaves the digester, is a combination of a material that did not get digested during digestion. This can be cellulosic material, high recalcitrant bond material that is left over, but can be ideal for other uses. The other, it contains a lot of the nutrients, metals, nutrients, alkalis. These don't break down during digestion. They leave as they entered. So it's just as valuable in the fact that the mass has been reduced significantly, which, if you think about it, the concentration's gone up in micronutrients. At most facilities, these go through an initial screening. This can be done through centrifuges, presses, filter presses, etc. But you usually enrich this solid material anywhere from 20 to high 20, 30% solids, and that can be sold off as a value-added product. We'll discuss the liquid, depending on the facility is, and the degree of treatment can be recycled back to the front of the process, which can be a critical component to these design systems, depending on where the system is at. Desert, arid areas that water is more of a resource, absolutely want to maximize how much return water they can bring in. Here, I won't spend too much time on it, but you can see on the left, it's a general breakdown of the degradation pathway of large organic molecules. All human bodies, anything really organic, can be generalized into three categories. There's proteins, there's carbohydrates, and there's fats. And then there's inert materials. And the combination of those together is what makes up living organisms. But you can make large projections and estimations based off chemistry and stoichiometry, based off of the empirical formulas of that. So on the left, you can see these molecules break down into monomers, sugars, and acids, into intermediate compounds, then eventually methane. And the big takeaway is that this first part, the breakdown, the one that we want to target during a pretreatment, like thermal hydrolysis, that's relatively the quickest to happen. The slowest is the last stage, is converting these liquid phase acids and alcohols into methane, the molecule, the money molecule, the one that drives the process. So that is the slowest, and the one that we really, all digesters are tailored to cater to. Everyone's trying to make that last stage and those bacteria as comfortable as possible. I won't go in this too quickly, but you can see on the left, this is a representative of a carbohydrate. Right here, this is a representative of the backbone of a protein molecule. All proteins are just made up of repeating units of this linkage with a different R group. Again, we won't get into the chemistry, but you can see just because nitrogen is part of that backbone, there's going to be a lot of nitrogen in a protein molecule. And fats and oils, these are fats down here. These are the chemical symbols for a long chain fatty acid, and this is a monoglyceride. Again, just representative molecules of what these three contribute to the biogas population. And the big takeaway here is that a digester fed with pure carbohydrate would yield 50% methane and 50% CO2. A digester fed pure protein would yield 70% methane and 30% CO2, whereas one that just had pure fat and oil would be 68% methane. This is important because you want to be very intentional about the ratios of the feed composition. Slaughterhouse material generally sits right around here. It's a great combination between fats and oils and proteins. We can get into the reason. I'll get into the reason later about why you can't have too much fats and oils or any of one thing, protein for another reason. But this combination right here, low in carbohydrate, yields the highest methane concentration of biogas in theory and practice. What conditions do the bacteria like? They like pH right in the middle. They don't like to go too high and low. Again, another good reason to EQ tanks, buffering systems to feed into the anaerobic digester. Temperatures. There's two temperature ranges, mesophilic and thermophilic, 35 and 55 degrees Celsius. The one thing that I like people to take away is that there is a valley between those two, that it's not one or the other or anything in between goes, that you want to be right at those temperatures in between there, because if your control is off, or if you're shooting for higher temperatures and it cools, there is very clear activation energy. It's called activation energy. The energy enzymes give to a reaction to reduce the energy it takes to complete it. But there's a clear valley here between the activation energy of some of these enzymes between these two temperatures of the critical enzymes in this reaction. Organic loading rate, that is the concentration of the organic feed being fed to the digester. You don't want it to spike too low or too high. Both are problematic. And again, this is more reason for that EQ and that buffering tank. And again, monitoring and routine quality control. Nutrients, there's a pretty critical ratio of carbon to nitrogen and carbon to phosphorus that should be maintained. VFA over alkalinity is another one. A lot of digesters just run on that alone. If they're in that range, they're fine. It's a buffer, a salinity and alkalinity buffer metric, but it's very important so that your digester doesn't go through large swings in pH. No oxygen, that's obvious, but critical. And micronutrients. A lot of plants don't run on these, but they can be huge benefits for biogas producers. And it's essentially bringing all of the levels of these metals and micronutrients for the bugs that require it. So it brings them up to an even level. You you test your material, see what you're off at, and there's a large number of companies here in the U.S. that will send you a recipe back that brings all levels up to ideal. Excuse me. This slide you can see on the bottom, the critical thing here is to tie the type of technology with the total solids level at the top. So as your total solids in a wastewater stream or food waste or manure system increases, it puts you into different categories essentially for your technology approach. The 0 to 5 really is the low level covered lagoons. These are generally characterized by less control. They are not, excuse me, they're often not heated. They're often not mixed. They're just stationary lagoons that are pumped into with a certain design residence time, usually significantly more because of the lack of mixing. Material comes out the back end and it's kind of a plug flow design. The biogas comes off the top and is processed. These are used a lot in waste remediation where the biogas generator is just flared. And I think, again, a lot of the reason for this webinar is to look at the options, again, for a lot of these facilities to see if waste to energy is the right move. Moving up from covered lagoons, you move into the CSTR or complete mixed reactors. These are the very common above ground large tank vessels that are very common in the Midwest or seen on farms or paired with industrial facilities. They have the bubble dome shape to them common. They range anywhere from 500,000 gallons up to I've seen 5 million gallon digesters. I'm sure there's bigger single ones, but above that, the plug flow digester, there's a lot on the market here, and they're very useful for their range in the total solids in the waste field. But again, that's very specific to the material you're using. And then above that, there's high solids anaerobic digestion, which there's very little water. It's usually the material's innate character is just being processed without additional water. So now I'm going to talk about the potential for co-digestion. So I think I've touched on a little bit the material coming out of these facilities. And again, all facilities are different, but has a tendency to be warm, be very high in soluble BOD, COD, the material that's useful for converting to methane. They already have water treatment systems, but the one kind of kicker outside of the potential inhibition by ammonia that needs to be addressed is that they're relatively low in total solids. That if you build a digester to process this volume, you're sizing it for the volume that's processed on site. It's not for how much organics are in there. You get as much biogas that is a function of the organics coming from the facility. So if you clean up the water less, if you do less upfront, more will be sent to the digester, you can make more gas. But in theory, a digester at that same scale and that same size could hold a lot more organics. And this is one of the things that I think are very interesting. A lot of these systems that I visited for slaughterhouses and meat industries, they flare the biogas because that's not the concern. But in the future, if this opportunity came up and if there was more, we'll talk incentive from the federal and state side, these systems with more kind of a hybridized design could produce a lot more biogas, could handle a lot more waste and produce biogas. So again, to improve digester chemistry, that's one reason to co-digest, boost biogas potential that I just talked about. The chemistry, just to note, a lot of slaughterhouses, it's those CP-CN ratios, carbon and phosphorus and nitrogen. Sometimes when you have that amount of nitrogen and protein coming in, you need more of a carbon source. So slaughterhouses can be co-digested with fats and oils from rendering facilities, but also energy crops, crop residues, bagasse, ground up. It requires some processing to get it into a state that's easily digestible quickly, but that can help your chemistry and more reason to bring in to make more biogas. The potential revenue from that, from the additional biogas is obvious, but another reason to do it if this was an energy production system. And then just maximizing your system design. Again, if you're a lagoon and you're building the system based and sizing it based off the amount of water processed, why not load it up with as much organics as possible to what publication and pilot testing says can handle? So it's essentially kind of the money on the table argument that if you've got a big lagoon and you're only treating at wastewater treatment levels, why not throw more into it if energy is of interest? Again, examples here, fats and oils, pre-consumer food waste, post-consumer food waste. These can often be great on paper because they bring in tipping fees. You're their waste remediation for a lot of these production facilities. Crop residues, yard wastes, energy crops. Biosolids is a trickier one. It's become legislatively prohibitive to land apply the end result of biosolid digestion. So that is trickier. But so here, now I'm going to walk into kind of the two main technologies that are focused for these water treatment facilities, and that's covered lagoon systems and CSTRs. So here in the first one, you can see a covered anaerobic digestion lagoon on the left being built. This is a plastic membrane liner that covers the bottom. These can be anywhere from a single layer of membrane to dual membranes with kind of mesh gap in between. They've come a long way in their design, so they're not as leak prone. They have systems in place that if a leak does form, any gas does not make these large bubbles in the bottom, but can escape through pathways and then be vented out through the sides. So lagoons have come a long way, but again, I think the takeaway is that they're often not mixed. They're not designed with mixing or heating involved, and those are kind of the two large design criteria to really push digestion to its limits. And when you do that, you push biogas formation to its limits. These are considered low-level technology, working with very low total solids concentrations. The HRTs can be very long sometimes because, again, without mixing, without heating, the one variable they have is time and size. So in theory, if cost weren't a factor, you can build these as large as you want. Eventually, material will decay, decompose. You will make methane, but again, at a higher cost and eventual cleanup costs as well. And because they're not heated, they kind of fall in ambient temperatures. On the right, you can see a photo of one operating under pressure with the methane gas, lifting the gas off of the liquid surface. You've got a flare system in front there. Flare systems are required anytime you've got the gas, because anytime, even if you're producing energy or RNG, if something goes down, you have to shut down. You need a place to revert that gas to for flaring, because gas is always going to be produced. That's one thing you don't have control over. Next slide, this shows a version of a continuously stirred tank reactor. You can see in the photo on the left, these are very common. You've more than likely seen them at farms as you drive through the countryside. These are considered medium level technologies in that they have all the control that you would see at higher level versions, but they're more passive. They can have, they're not as, what would be the word? There's not as heavy mixing involved in here. It's more pump mixing. It's more mechanical mixing. It's not large, high amp motor mixing like a solids digester. So you can see in the right here, this is a version of an eduction mixing system where the material is sucked from one nozzle inside the tank and forced through small outlets called eductors, and it's a shear force mixing. Right here, you can see a version of an internal mechanical mixer where it's just a prop like a boat. Above that is a version of an external heat exchanger. So the material is pumped from the inside through these tubes on the outside of the reactor, and they go through a counter current heat exchange, heat up the material, inject it back into the system so that the entire liquid phase, when it's mixed, stays at one constant temperature. And this mixing and heating is what allows these digesters to perform continuously even through the seasons. It can be in the middle of the Wisconsin during the middle of winter, but as long as it's insulated and heated properly, the performance should not fall down too significantly. Digestate processing. So after you've done your digestion for X days in the digester, technology depending, you've got to go through some type of separation stage for the material. You want to separate into a solid and a liquid phase, especially if you're going to recirculate that liquid phase back to the digester. When you do have that in the design, though, there is a lot of intention that goes into the concentration. Sometimes it's called a solids retention time. There's hydraulic retention time and solids retention time. And the hydraulic is just the amount of time the water spends in there. The solids, depending on the way that you screen it and concentrate it once you leave it, can be recycled back to a degree to increase breakdown, digestion. It essentially increases the amount of time solid material spends inside the digester, which you can play with to increase your gas production. But everything comes with a cost. So that in that case, it would be pumps running at higher speeds more often. So, but in the first stages, there's a whole number of options and technologies associated with just the organics removal. screening, clarifiers, what's it called, hydrocyclones, centrifuges and decanters, coagulation, flocculation, all the way to drying once you've got it separated. There's biological treatments post-separation that you can treat the water for, waste stability lagoons, trickle filters, rotating biological contactors, activated sludge systems. So depending on the end use, the end goal, where is this wastewater going to, will dictate the degree of treatment post anaerobic digestion. But again, the takeaway is there's a coarse and a potential fine treatment stage. Coarse would just be the physical screening, and then you'd move into fines treatment. Value-added waste streams. So now that you've got these two streams separated, your 28% total solids digestate, your water, plus or minus, again, that depends on the degree of treatment, what to do with them. The solids are used very commonly as a nutrient-rich solid, as a fertilizer, as a soil amendment. In the case of dairy farms that aren't using sand bedding, that are using an animal or a hay bedding, that material is often dried and recycled back as a bedding material for the cows to supplement additional new material being purchased. The water itself is recycled most back to AD. That's a very common design desire. Again, it reduces your well water usage, your treatment of that well water, keeps things in kind of the circular economy as much as possible. But the water, again, it's not as concentrated as the nutrients as the solids portion of it, but there's absolutely soluble nutrients in there. And if you can partner with a nearby field, that's all the best, because travel ultimately with anaerobic digestion is a barrier. You want to limit the amount of travel and time the material spends to get to the facility, but also you don't want to send it away any distance, because all of that just takes away from the benefits of the circular economy. If there's a local farm, if this is on a farm, you want to make as much efforts to keep this used, and on in-house. And then the last option would be sewer discharge to a local POTW. So now we come to the biogas. We've talked about the digestate, what to do with the liquid and the solid portion, what do we do with the gas. As I mentioned, commonly right now, a lot of these lagoon systems at slaughterhouses will just be flaring their biogas. The low-hanging fruit would be thermal energy. If this was an animation, that would be the only one showing right now. But thermal energy essentially is retrofitting their boiler to be able to co-generate heat off of natural gas and methane, which is natural gas, just not cleaned up to the degree that's coming out of your stove. This has a lot of benefit, and there is legislation coming through the pipe, and I know I don't know enough about it, but there's a thermal credit coming online that I think is going to be a real benefit to a lot of these operations, that if they can factor in this thermal credit, offset their natural gas usage, and get a thermal credit from the government, it may be much more attractive in the future to pay for some of these systems. So cogen in the boiler. The other option, combined heat and power. So this is actually an electricity generation method, the combined heat and power, but one of the byproducts of electricity generation is a lot of thermal energy. So when these systems come online, these CHP systems, you're generating electricity and you're also generating thermal energy. I've seen examples of this where that thermal energy is completely dedicated to the heating of the AD material going into the system. So they don't even bother using that heat back into the plant. They keep it outside near the digester, and then just exchange that, economize that with incoming water. The second option, electricity. This can be done a number of different ways. The most prevalent is the gas turbine. Fuel cells are also commercially available for biogas, and then steam generation through electricity through steam generation. Each one requires its own unique kind of cleanup standards for cleanup, which means the degree of treatment for the biogas, removing siloxanes, oxygen, nitrogen. In some cases, cleanup is less intense for the thermal energy. You're really essentially knocking out a lot of the moisture and the sulfires, hydrogen sulfide components there, whereas electricity and renewable natural gas require quite a bit more innate treatment to the biogas for processing. The systems that the processing and upgrading equipment is expensive enough that you do not want to foul it prematurely. But gas turbines are run to design. They can get about, I think the efficiency is around 1 kilowatt from about 8,800 BTUs is around a gas turbine generation plus or minus. I don't remember fuel cells. I think that's a bit more efficient, but the cost is there as well. And then renewable natural gas as the last option. The draw for renewable natural gas is it's very profitable. It's a very widely accepted system. These pipelines are everywhere. They do cost a bit. And to justify that cost, the system needs to be of a certain size. The limitation for a lot of systems is they just don't produce enough biogas routinely to justify the cost. But for larger systems, larger operations, and especially ones that are that have potential for co-digestion of really boosting their biogas potential, this may be an option for the future of the kind of, in my opinion, the next phase of digesters to come online. Biogas upgrading and utilization. Just touching on that renewable natural gas, because again, these are the bigger systems. These are the large slaughterhouse operations, the multi hub and spoke models that could draw from multiple facilities that have this potential. You can see in the corner here a image of a small upgrading treatment system. But a lot of these incorporate several technologies: pressure separation or membrane separations for CO2 separation, pressure swing absorption for nitrogen separation, amine scrubbing, water washing for particulate, H2S removal. They may be iron sponge that required. But ultimately, the takeaway is that it's not just one thing to get this to renewable natural gas stages. There's multiple technologies that require monitoring and telemetry. So these systems can be costly. So there is a limit to them. They need to be cleaned up. RNG quality is usually around 98% methane. Absolutely no O2, anything in there that could oxidize or degrade the pipeline. Because again, the U.S. has thousands of miles of pipeline across the U.S. They can't afford to have any of it damaged by poor quality gas. But again, there's a very profitable, very large industry here in the U.S., renewable natural gas. So federal incentives. I'm going to finish up the presentation today by talking a little bit about the current federal incentives, state, and other opportunities to help funding for this work. Admittedly, the first of this year has not been great for renewable energy. There's been a lot of things administratively and out of my control that haven't spurned it. But traditionally, the last 10 years have been terrific. There's been a huge amount of anaerobic digestion coming onto the market. In the last 5 or 6 years, I'm not sure when the investment tax credit came out, but that was a huge boon, offering up to 30, up to 50% sometimes based on eligibility CapEx costs for installing anaerobic digestion systems. That has recently changed. The legislation has changed on that. I don't know where it currently stands and what percentage, but I'm a big advocate that gets replaced, retroplaced, whatever the term is for it, but reinstated. The production tax credit, if you're producing electricity from a renewable source like biogas, they give you a tax credit per kilowatt hour. The renewable fuel standard mandates the use of renewable fuel standards and biogas for transportation use. Rural Energy for America program, this is a very popular grant and loan system for rural systems and industry, commercial entities to apply for AD systems, and for farms, egg systems as well. The clean fuel production credit, again, if you are able to produce the biogas for sale as a transportation fuel, like biogas, I don't know where these credits are in price or percentage of the project, but I see them accounted for in almost every financial pro forma I go through, and they are a considerable part of the revenue streams when accounted for. The Biomass Crop Assistance Program and the Inflation Reduction Act. The Inflation Reduction Act was large. It offered tax credits for biogas production for non-electricity generating. So these ones, that credit was able to apply for things that weren't transportation related, which I think a lot of the rural operations were more interested in. State incentives. The low carbon fuel standard in California has been a terrific program, helping a lot of industry grow there. And because of its success, there's a lot of states looking to adopt a similar model program. I know Minnesota, Washington, there are a few others I'm forgetting, but it would be terrific if that spread as well. Renewable energy certificates. These are certain states have portfolio standards that require RECs being traded for compliance. For certain industries, renewable identification credits can be purchased and sold, similar to carbon credits, carbon offset credits we'll talk about. Grants and cost sharing. Many states offer grants and cost sharing programs to support anaerobic digestion specifically. Tax exemptions, same. Some states offer these tax exemptions or 480 systems for the land purchasing. Net metering allows small-scale biogas producers to sell excess electricity back to the grid. And then again, non-state, but other incentives, the carbon offset credit, voluntary market for trading carbon credits that can be generated from biogas production, and lots of different financing options I've seen, from grants, cash reimbursements, and loan guarantees available out there. So, and my last slide is just on the general stages of future AD project development. If a facility is interested, how do you understand whether you are right for this? If AD is right for you, where's the cost benefit? And the first thing is a feasibility study to look at the logistics, look at the size, and look at the equipment that would high level be involved to integrate that waste stream into an anaerobic digester. I am a big believer that always needs to be paired with material testing and pilot scale testing if time allows. There's no certainty in taking these values from publication that your material is like the material that was tested at one time. Trust me, I've done so many lab scale BMP and pilot scale testing for AD that it's really hard to recreate it from the same material sometimes, let alone just taking it from publication because it's similarly typed. So you really want to be using empirically derived test data in a lot of your projections, and especially with something like slaughterhouse and commercial industry processing facilities where timing doesn't necessarily match up a 24/7 operating digester. You need to make sure that in the middle of winter, your production is as expected versus right after a CIP event or right after some type of logistic anomaly. So that is always critical. And then once you've done your material testing, you feed that back into your feasibility study and your economic model for refined economic modeling. And once you have all that done, and everything's cleared, then you can move into engineering design. And if your plant is just looking for optimization or retrofitting, that is something that's very critical as well. I mean, you may have a system already, you're producing at 50% of what somebody said you could. How do you determine what your actual potential is? And it's very easy to go in there and do put those metrics together to do performance analysis. So, with that, I'll say thank you very much for everyone who's attended and stuck through it this long, despite technical difficulties.
And just enough time for you to answer them.
Perfect.
What are your thoughts on managing long chain fatty acids to maintain digester stability and, importantly, keep the biogas production up?
Yep, a good question. So fats, oils, and grease, long chain fatty acids that you're talking about, they're really great for making biogas, but they can be inhibitory. They can be toxic to a point. So at least understanding the innate composition, and if there's a co-digester situation where you can bring in additional ones, it's understanding the highest concentration possible during that feed. And if you've got a co-digestion, it's about controlling the feed of that material into your effluent feed. So monitoring that with some type of position control valve or PLC, that you don't feed more than X pounds of this or percentage of pounds relative to what's gone in that day from your system. So with telemetry and control, that can be dealt with very easily. So you kind of stay at that high organic feed level. Yeah.
In between keeping everything in between the waves.
Right. Yep.
Could you work with multiple substrates during a feasibility study?
Yeah, absolutely. And that would be, especially if the facility has multiple byproducts. So they've got a DAF on site and they don't know if they can use the DAF solids because of the chemical they're using in their DAF, and they just want to use that. What we've done traditionally is test everything on site. Everything's being produced from the DAF solids, the effluent. You do a BMP test, see its potential for biomethane. If it's there, then you run into a pilot scale testing, because you don't see inhibition in BMP testing. You just see biogas potential. The inhibitors are diluted out in the methodology. You actually need to feed a digester continuously to see what the actual steady state levels of these inhibitors are. And that's why, based off early characterization of all those different streams, yes, you'd absolutely want to do as much parallel testing with different substrates.
Okay, thank you. Yes, from a practical perspective, what is the critical cost component in any biogas plant design?
That's a good question. So you're asking about the biogas plant design, and if that depends if the anaerobic digestion is part of that biogas, because you can have a biogas plant from landfill gas, what have you, but usually the equipment across the board for biogas for an anaerobic digestion system, or across the board for all of it, is around 35% of the total project cost. It can be 30 to 50%. The digesters are about, there's rules of thumb for this. And again, this is a big plus or minus for rule of thumb, but you can look at about what was it, $1 per gallon installed cost on the tank itself. Again, this is just, I'm throwing a number out from a CSTR rule of thumb, above ground tank. For energy systems, electricity, if you're generating electricity, there's a number commonly used in the industry of about $1,000 per kilowatt based off of your production potential. But yeah, you're looking at the big costs are the digester itself, and then the energy upgrading, whether it's electricity, it's the cleanup and the energy generation, or the RNG upgrading equipment. There's not as much in the boiler modifications if you're just doing the digester to a boiler. That a lot of the times, and newer boilers out there have either kits or the ability to be retrofitted with ease relative to for co-digestion. So yeah, it's hard to break that into a percent cost, but the digester itself. And then again, pre-treatment can add a whole nother cost. If you have to add in a thermal hydrolysis system, that's a whole nother tank with mixing and the same kind of controls that would be on the digester, just smaller.
So again, driven by your goals.
Yeah, completely goal driven.
Yeah.
If you're looking to produce
and
energy,
very unique to every industry and plant. And again, I thank everyone for joining us. Thank you for your presentation, Dr. Anderson.
Thank you, Diane, for helping set all this up very much. I really appreciate it. And I'd like to thank Todd DeJornett as well for his part one in the series, and his he kind of helped bring all this about. I was glad to be a part of it.
All right, bye-bye, everyone.